Hello guys, so welcome back to our discussion about others. So we explored last time the half other and many designs for the full other, okay? And now we have another example. And now we're gonna, build upon what we have studied, basically the full other and the half other, okay? Half other and full other are really a foundation, really basis that you can use a lot in, arithmetic logic units, we can say in processors, okay? So for example, let's design now what's called the binary adder. A binary adder basically is a circuit that can add two binary numbers together. These numbers may be more than one bit. For example, here we want to add two numbers, A and B. This guy is 4 bits, and the other guy is also 4 bits, which is B. Okay, so basically you have, 8 inputs. So you have 4 bits for A and 4 bits for B. Okay, how many outputs? Let's see. So just try to add the maximum of each. So 4 ones and 4 ones. This is the maximum for A, this is the maximum for B. So this will be 0, and we have a carry of 1. This is 3, 1 and 1, 1 and 1, then 1 and 1, then finally 1. So we have 5 bits, 4 as sum and 1 as carry. So here is the outputs, 5 bits. And now let's, do what we have done so far. We're gonna start first by the, the scratch, like what we have done with the full other. The full other, we design it in 2 ways. The first way is starting from scratch, build, truth table, and then kind of maps, many maps, because you have many outputs. Here you have 5, for example. And then we build or implement the circuit. Let's see if we can do that here or not. So basically you have 8 inputs and we have 5 outputs, okay. But if you have 8 inputs, how many combinations you have? You have 2 to the power of 8, which is 256 combinations. That's really, cumbersome. It's really difficult, for a human to do such combinations. And even if you do this, then you will have 5 functions here. And you need to do 5 Karnaugh maps for each. I'm sorry, 1 Karnaugh map for each. And this Karnaugh map will be also cumbersome. It will be basically 16 4x4 Karnaugh maps. Okay, 16 4x4 Karnaugh maps. Remember, for 4 variables, we have 1 Karnaugh map 4x4. For 5 variables, we have 2 4x4 Karnaugh maps. For 6 variables, you will have 4 4x4 Karnaugh maps. For 7 variables, you will have 8. Then for 8 variables, which is our case, you will have another 8. So you can do that. And if you did with tabulation, that's okay. But again, for a human to do that, it will be also difficult. You must build a program, a CAD program to do that for you. Okay? So basically here, starting from scratch, like what we did with the full other, is not a viable solution. Okay, and we need some more smart way. And the smart way is basically we highlighted before. It just is a structural model or the behavior, or the hierarchical model. So let's think about this example here. Here we have 2 bits. Okay, this can be done using half other or full other. And here we have 3 bits, which is basically, can be done using a full other, or even maybe, or even more than 1 half other, like what we see with the full other. So if you have the half other design, which is, a small design, we can say a base for you, then you can build a package out of that guy, then you reuse it in such design. And here is the design now. Here is, our 4-bit binary adder. So we will do each operation here with a full other. So we need 4 for others. 1 for this one, 1 for this one, 1 for this one, and 1 for the 4th. Okay? You may say this is a full other one, which will add A0 and B0. But remember, there was no carry here. If we look back, there is no carry for these 2 bits. So basically the carry will be 0. And you must not leave it float. You must connect it to anything. Any input float in the circuit might get unpredictable, noise that may cause it as a logic 1 or logic 0. So you must connect it to 0, to the ground of the circuit. Basically, this is a circuit, okay? And 1 is just the VCC of the circuit, the high voltage, and the 0 is just a ground. And then, look, what happened here? We have a sum of 0 and then a carry of 1. So the sum will be just one of our outputs. Then the carry will go to the other for other. This carry here will go to the second full other that were summing these 2 bits. And remember, the full other can add 3 bits together. So it will add now A1, B1, and C1. This will give you another sum, then another carry that will be added with A2, B2, which is basically, this is C2, and this is A2, B2. Then this will give us S2, then another carry, S3, C3, which will be added with A3, B3. So the final carry is here, which will be added with A3, B3. This will give us our final sum bit, and finally the total carry of the operation. Okay, it's really very very easy. Even in the coding here is just 4 lines. So when you build your design in VHDL, for example, and you have the architecture, this will be 4 lines. In these 4 lines, we're gonna instantiate 4 full others like this. Okay, so that's basically one way to design this binary other. Okay, also this design is really modular. You can extend it to whatever number of bits you have in the input. Okay, for example, you can if you want a 6-bit to add 2 binary numbers, 6 bits, so you just add another 2 full others. It's really easy to extend. Even if you have this input before and you have now 2 new numbers, 2 binary numbers that are less than 4 bits, it's also easy to use it, basically, because if you have, for example, another 2 numbers like let's say M and M, okay, each one is just 3 bits, like M2, M1, M0, N2, N1, N0. You can still use the design if you have it already, and you will just put here 0 and 0 for the M3 and N3, which is not there basically. Okay, and you connect M2, A1, M2, M1, and M0 to B2, B1, B0, and for example, the ends to the A's, N2, A2, N1, A1, N0, A0. And you just leave the final full other with inputs that are 0, connected to ground. Again, you cannot leave an input just a float. You must connect it to something. And of course, here you must connect it to 0. Okay. One problem with that design, although it's really good, extendable, tractable, you can trace it really easy, is that there is a delay between the appearance of each output. So for example, so here in the full other one, okay, S0 will appear, then C1 will be outputted from that full other, and then S1 will appear only when C1 enters full other 2, and again for S2. So S0 will appear first, then S1, then S2, then S3, and so on. And that's a problem, because if for 4 bits it may be not that huge problem. But if you have, for example, 60, if you are adding 64 bits together, I mean 2 binary numbers, each one is 64 bits, then the output or S63, because we start from 0, will appear after big delay. So for example, if the delay here is delta t, then this appear after delta t. This is 2 delta t, 3 delta t, and so on. Stage number n will the delay will appear after n delta t. If n is big, then n delta t will be also big, or might be also big, or not good for your application. So in the next video, we're gonna tweak our design such that we get still hierarchical structure design, although it will be much faster than this, and you will have the outputs, all the outputs appears together at the same time. So stay tuned, guys, for this video. Thank you very much. Bye bye.